Hi, my name is Fernando. I'm a professor at the UFMG in Brazil, and today I will present to you the paper Exploring the Space of Optimization Sequences for Code Size Reductions, Insights and Tools. That's a work that I did in collaboration with Bernardo Lima from the Federal University of Minas Gerais, he's my colleague, and with Anderson Faustino from the State University of Maringá, that's in the south of Brazil. So the main goal of this paper is to describe a strategy to explore the space of optimization sequences for code size reduction. In this paper, we introduce the notion of optimization cache and covering set. An optimization cache is a table of programs to optimization sequences that can be used to support a predictive compilation. Entries in this table are numeric representations of programs. These entries are mapped to sequences of optimizations that are good for that program. The covering set is a small ensemble of optimization sequences that, once combined, they tend to be good for any program. In our study, we found 22 small sequences for LLVM. These sequences they're good for code size reduction. So if I have a program, at least one of them will sort of be effective to reduce the size of that program. To build the optimization cache and to find the default covering set, we had used a large set of benchmarks. A large set of benchmarks is necessary to explore the space of optimization sequences for code size reduction. And to do that, we chose EngaBench. This is the largest collection of compilable C programs that's publicly available today. This space that we need to explore is formed by every possible sequence of optimizations that can be applied onto programs. And note that the same optimization can be applied multiple times onto the same program. And thus, we can have some very large sequences of optimizations, like this one produced by Clang minus OZ. OZ, in this case, one of the default optimization levels of the Clang compiler. And we can have short sequences as well, like this one here. So any vector, any list of the sequences is a point in the search space of optimizations of the LLVM compiler. And such a space can be defined for any compiler. It suffices to build all the possible combinations of its optimizations. So notice that the optimization space is infinitely large. For the same optimization can be applied multiple times on the same program, always with new effects. And to understand a bit better this space of optimizations, we need benchmarks. But we want programs that are likely to be representatives of every program that could be written. And of course that's impossible. But so at least we would like to have representatives of every program that could be written by a rational programmer. So we need a way to get representative benchmarks. To get these benchmarks, we filtered them from a collection with 1 million compilable C programs. This collection is called Enga, and the Enga benchmark suite. To perform this filtering, we started selecting the largest 15,000 programs from Enga. Size in this case is measured in number of LLVM instructions for programs compiled without any optimizations. From this lot of 15,000 programs, we selected 1,500 representatives. For this purpose, we clustered the 15,000 programs. To cluster them, we transformed them into vectors. These vectors are formed by program features, like number of loops, number of arithmetic instructions, and such and such. These features were defined by Namularu et al. In 2010. These vectors consist of 56 program characteristics. We use k-means to find these 1,500 clusters. So out of the 15,000 benchmarks, we got 1,500 representatives. In other words, k-means will give us 1,500 centroids among these 15,000 vectors. Each centroid will be a representative program. So we have now a benchmark suite with 1,500 programs. The hope is that these programs contain a good variety of program features. With these benchmarks, we can start playing with the optimization space. For instance, the probability of finding good optimization sequences by randomly sampling the optimization space is non-negligible, albeit small. In other words, let's pick up a program. Let's call it P. Any program would do. Now let's compile this program with opt minus OZ. OZ is one of the two default optimization levels in LLVM used to reduce code size, and opt is the LLVM tool that applies optimizations on the intermediate representation. That will give us an assembly file. Let's call it O. Now let's look into the universe of possible optimizations. This universe is infinite, of course. Let's then only consider the subset of this universe formed by sequences with 100 optimizations. Now let's draw one random sequence from this universe. Let's call it S. Now if I apply S onto P, then I will get a new assembly file. This file will be called O prime. It's likely that O prime will be different from O. Given these definitions, the probability of having O prime, the program produced by S, being smaller than O is about 10%. That's the expectation of beating opt minus OZ for a given program. We can arrive at such results given a sufficiently large number of benchmarks as a consequence of Chebyshev inequality. If you want to know more about this methodology, you can read our paper, but just as a spoiler, Chebyshev inequality is the reason why I have to choose 1,500 programs. Anyways, because there are so many points in the search space, finding good optimization sequences requires some guided methodology. As an exercise, let's contrast a guided exploration methodology with random sampling. To this end, we chose to evaluate the implementation of a classic genetic algorithm provided by the Pygmo library. That's implemented in Python, the Pygmo library, and it's open software. It's very nice to play with generic algorithms. The first question that we can explore is how effective is the genetic algorithm as a technique to find good optimization sequences? To answer this question, we will use our 1,500 Centroid programs. Testing random sequences, where for each program we draw them anew, these random sequences, whenever I produce a new random sequence, I'm drawing them anew, meaning that they can have repetitions, but it will only happen by chance. Anyways, now we can experiment with the genetic sequences. To try to find good optimization sequences, we will start with 100 individuals. Each individual is an optimization sequence with 100 elements. So the crossover probability is 0.9 and the mutation probability is 0.1. And now let's see how effective is the genetic algorithm as a technique to find good optimization sequences. This figure shows the number of times each method wins, including ties, in a universe of 1,500 programs. Our X here means drawing X random sequences of 100 optimizations per program. So for instance, R50 means drawing 50 random sequences of 100 optimizations. Thus, these results indicate that LLVM's default optimization levels are roughly equivalent to drawing 50 random optimization sequences of 100 elements each. In addition, the guided methodology is substantially better than random sampling. The availability of a rich suite of benchmarks offers invaluable support for predictive compilation. In this way, we use the 100 programs, the 1,500 programs to build a map of programs to optimization sequences. An optimization cache associates a program, P, with a list, L, of optimization sequences. Sequences in L are ordered by the benefits that they bring when applied onto a program. In our study, we developed a methodology to build optimization caches. This methodology is parameterized by different tools, which are previous work. The searcher explores the optimization space to find, for each program in the training set, optimization sequences that are good for it. The sequence reducer simplifies the sequences, removing the passes that do not contribute to code size reduction. The program reducer is an algorithm to simplify the programs in the benchmark collection. Program reduction must ensure that good sequences remain good for the simplified programs. Notice that all these tools, they have been published in previous work, like in PLDI, for instance, and other papers. The merger is a post-processing phase used to merge simplified sequences and programs into a final table that associates programs with lists of optimization sequences. We have augmented LLVM with the capacity to choose optimization sequences for programs. To this end, we have adopted the customizable skeleton of a predictive compiler. Like the methodology to build the optimization cache, the way to use it, to carry out predictions, can also be parameterized. This parameterization is not actually a contribution of this paper. It had been noticed already in 2018. However, to make such a strategy practical, we have modified it in several ways. In the first step, the predictive compiler extracts a vector of numeric features from the unknown program. Next, the predictive compiler finds the closest program P from the optimization cache to the unknown program. Similarity is measured as the Euclidean distance applied on feature vectors. Finally, the predictive compiler applies onto the unknown program the first n sequences associated with the closest program that we call P, keeping the best result. N, in this case, is also a parameter of the predictive compiler. We can investigate the effectiveness of the predictive compiler based on the optimization cache. This figure reports relative variations in the number of LLVM instructions produced by either the baselines, here I'm adopting 4 different baselines, or by the predictive compiler. Each number on the y-axis is the variation on the number of instructions, the average variation. We are looking into the average variation for programs in the MyBench collection. That's a suite with 30 programs. So we have trained the optimization cache on NGAbench, but we're validating it in MyBench. Negative numbers mean that we increased code size on average. Positive numbers, in turn, mean that we reduced code size. And as you can see, most of our results, they are fairly positive. Notice that we are varying the number of sequences that we apply on the program. We can apply, say, 22 sequences and then keep the best result. That means that I take the 22 best sequences for the known program P, and then I try them all on the unknown program, keeping the best result. If our predictive compiler uses only one optimization sequence, the results, they are worse. They tend to be worse than the baselines, except for OPT minus OS. However, as the number grows, the quality of the code thus produced improves considerably. By varying n from 1 to 22, the predictive methodology really starts reducing the size of the assembly programs. In this last experiment, we have been using reduced programs. They were produced with C-reduce. It's a tool we used to simplify bug reports that have been published in PLDI before. If we use the original programs, which are much larger, as entries of the optimization cache, then our results, they're better. But in this case, the process of building the optimization cache is more expensive because the programs are larger. As you can see with the original programs, most of our results are on the positive side, meaning that we have been able to reduce code size. In the end, our study reveals that default optimization sequences adopted in mainstream compilers, they tend to be good for most programs when compared with random optimization sequences. However, the sequences can be very bad for some programs. So, how many default sequences a compiler should have in order to provide at least one that's good for any program with high probability? The small set of sequences that contains at least one good sequence is called the default covering set. Finding a default cover set might not be possible because the baseline might outperform every other optimization sequence for some program. Yet, there are some heuristics to find covering sets. We have used Pirini's algorithm to find sequences for code size reduction. To find this covering set, we start building the so-called performance matrix. In this matrix, the rows refer to training programs, and the columns refer to candidate sequences. So Mij is 1 if sequence j beats the baseline for program I. Using Pirini's algorithm, we got 22 sequences that almost cover all our set of 1500 programs, the centroids from 4. Some programs could not be covered, actually because the baseline was already the best for them. And now we want to analyze the quality of the code when we use our 22 good sequences. The question is, how effective is our cover set when compared to the baseline sequence? As baselines, like before, we have used clang minus OZ, clang minus OS, OPT minus OZ, and OPT minus OS. Usually, clang minus OZ is better than, say, OPT minus OZ. And that's because clang can add some optimization guiders in the program's IR. I mean, clang is somehow language dependent, it's for C, and OPT is sort of language agnostic. This figure shows the average variation in the number of LLVM instructions produced by our covering set when compared to different default sequences. Here I'm using different numbers of sequences in the cover set. That's in the y-axis, x-axis, I'm sorry. So the cover set yields better results than the optimization caches in general. On average, when using the 22 sequences, it leads to code that is shorter than OPT minus OS. And we tend to beat clang minus OS by a larger margin. And we are also doing a bit better than OPT minus OZ, and a tiny bit better than clang minus OZ. We reduced programs by 47 instructions on average. And here I'm talking about programs that have like sometimes 300,000 instructions. But notice that the comparison is a bit unfair because we use OPT to run our sequences. Clang minus OZ adds some pragmas like non-on-row and non-inline to the program, which we cannot use. The good comparison is done with OPT, and in this case we do much better. To use the cover set, we apply the same sequence of optimizations on every function in a file. These sequences, they have been obtained through training over individual functions. Hence, it's expected that their relative improvement decreases as programs grow. So we want to investigate how the relative improvement of the cover set over other approaches varies as programs grow. This figure shows this variation. The red line shows the ratio of code sizes, like a number of instructions produced by clang minus OZ divided by the cover set. The bars show the benchmark sorted by the number of instructions. When compared to clang minus OZ, gain is decrease indeed, as the number of benchmarks increase. Remarkably though, for the two largest benchmarks, consumer typeset and ops ghost script, and here I'm talking about the mybench collection, the cover set still outperforms clang minus OZ. A work that's especially close to ours, in the sense is Jain et al.'s study of the optimization sequences used in OPT minus OZ. The authors, they have grouped the 70 or so transformation passes found in this OZ sequence into 7 categories. These categories contain, in the view of Jain et al., combinations of passes that are related by their effects on the programs. The 7 categories of optimization proposed by Jain et al., they can be combined. Not every combination is admissible in the original paper. For instance, GF, which is one of their categories, must precede any sequence. Anyways, Jain and all, they report results for 6 combinations, which we utilize to compare to our covering set. Comparison with Jain. Here, this figure is showing this comparison on the number of LLVM instructions. Our cover set yields smaller codes than the best of those 6 categories in 27 cases, and it loses in 3. If we compare our default cover set with the best of all the 19 ways to combine the groups, ways that make sense for some combinations are impossible, then the cover set wins in 22 cases and loses in 8. And so I think now I'm going to conclude the paper. And so we have explored the optimization space of LLVM 10.0 that's guided by this objective function that tries to minimize code size. Among the insights that we have acquired in this exercise, we mentioned the observation that the default optimization levels available in the compiler, -OS, -OZ, they are good for most programs. However, they perform rather poorly for a few. Throughout the paper, we have discussed 2 strategies to improve our default levels: the optimization caches and the covering sets. The 22 sequences in the default covering sets that we have produced in this paper, they are rather small. They range from 5 to 19 optimizations, with an average of 11 optimizations. And furthermore, techniques like those described in our paper, they can be used to find effective default sequences for other compilers. We don't have to be restricted to LLVM or to the C programming language. And applying all of them onto a target program to choose the best results is not really impractical because the sequences are small. Therefore, we believe that such sequences can be incorporated into the toolset of LLVM, for instance. And if you are interested in our work, please, you can get in touch with us. Our code is publicly available in case you want to contribute or use it. And we have an artifact available at Zenodo 2. And with that, I conclude the presentation. Thank you very much for your attention.